Hello everybody, and welcome to this lectures on computer architecture. Today I will take another look at the master-slave flip-flops, and specifically D-type master-slave flip-flop. Will be a complete, nice, full sentence at the end of this lecture, and I hope you will then understand what all this confusion is about, and you understand what this entire full phrase actually means. So let's kick off, let's take a look. First, we have to actually present a very important circuit, because normally all our electronics actually they respond to input states. And we've already said that there are some types of electronics that do not respond to input states, but to changes of input states. And we say this, that it's, for instance, it responds to the positive flank of clock pulse. So actually, that is not completely technically correct, but we will also use this jargon, but it has to be explained a little bit. So actually what is going on here is, if we have a clock and we pass this clock directly to an AND gate, and we pass it directly to this AND gate, as you can see here, but we also pass it through a NOT gate. So we get here the clock and we get the NOT clock, and ending them, of course, it should always be 0, because it's either this one is 0 or this one is 0. They cannot both be 1, so the output here will always be 0. However, this NOT gate also introduces a small delay, a small delta t, let's call it. And in this, that the NOT clock is a little bit later than the clock itself. So we have here a very short time that both the clock and the NOT clock are 1. And if we pass this through the AND gate, then we will get a very short time, we get a 1 at the output here. And this delta t, the width of this pulse, is determined by the delay of this circuit that we have here. And as you know, nowadays they can make transistors that are easily in the picoseconds range. So we can make this thing very narrow. And if we're going to use this for our signals, for our gate, as we will see, then effectively it is behaving, of course, to the 1 of this gate, but that is only in the beginning of the clock pulse. So what we're actually going to say, abbreviate this, is saying, well, our circuit responds to the rising edge of the clock pulse, which is not correctly true, technically not correct, because it's just responding to this 1 that we have here, but that is in the beginning of the real clock pulse. So we can say this, yes, it is responding here to the rising edge. So let's take this, keep this in mind, and now go back to one of our circuits, one of our gates. This was called the JK latch. Remember, a JK latch is a set reset latch with the combination of set equals reset equals 1 allowed. And now they have different names for that, so they're no longer called S and R, they're called J and K, but basically it's the same. So what do we have here for the truth table of this circuit? That if J and K, that is set and reset, are both 0, then the output is maintained. So Q, that's the output, remains at the state Q, whatever it was. And if J equals 0 and K equals 1, that is a reset of the output, so there will be put a 0 on the output. And if the input is 1, the J input is 1 and the K input is 0, then this is equivalent to a set of the output, so the output becomes 1. And if they are both 1, for the JK this is allowed, the output is toggled, so if it was 0 it becomes 1, and if it was 1 it becomes 0. So this is nothing to do with the flanks of clock pulses or whatever, because this circuit doesn't have any clock, it just has these 2 inputs. It's not gated, it's not clocked, it is just a latch. So it just behaves, it's just a logic gate, but it has memory effect because of the feedback, as we have seen in previous lectures. Now let's complicate this circuit a little bit, and instead of supplying directly J and K to our JK latch, we actually put a gate in between. And this gate is actually consists of these two AND gates. These are AND. And that means that if the gate is 0, whatever J is, this J supplied to the JK latch is 0 and the K is also 0. Simply this gate that is 0 blocks through these AND gates, it just blocks them. They don't arrive, the J and K signals, they don't arrive at the JK latch. So that means that if the gate is 0, whatever JK is, it doesn't matter because it's disabled. Actually the output, it is as if 0, 0 arrives at the gate, and we know from the previous slide that this means that Q actually remains at the state Q. The output is unchanged. However, when the gate is high, then the J is passed to the JK latch, and we have a normal truth table of the JK latch, meaning 0, 0. The output is remained, 0, 1, this is a reset, 1, 0, that's a set, and 1, 1 is toggling the output. It means you can sort of enable the JK latch by a gate signal. Okay, let's complicate the things a little bit. Now I will put it in such a way that K is always the inverted signal of J. And let me now call this D, because this is called the D latch. So the D latch is that J equals to D and K equals not D. So what do we have then? We have that if the gate, like the other one, if the gate is 0, then it doesn't matter what D is, the output is maintained. However, when the gate is, this should be 1, if the gate is 1 and D equals 0, let's take a look at the previous slide here. If D that is equal to J, and this was not D, if D equals to 0, then of course J equals 0 and K equals 1, and that means that we put 0 at the output. And if D equals 1, then J equals 1 and K equals 0, and we place a 1 at the output. This combination is not possible, and this combination is not possible. So we get this kind of behavior. If the gate is 0, the output state is remained. If the gate is 1, then the D is copied to the output. So if D is 0, output becomes 0. If D is 1, output becomes 1. So what do we have here? We draw this box. We have a gated D latch. So we have here actually our gate signal, which I forgot to draw here. Let's complicate the things a little bit. And now, I didn't want to show you this. I've been practicing a little bit what I want to say here. So what are we going to do now? Now we're going to use our funny clock signal, which was this circuit that is here. Remember, this converts the clock into small pulses like this, and the circuit only responds when this pulse is high. So that means on the rising edge of the real clock pulse. And that means that at that moment on the rising edge of this clock pulse, then the input will be copied to the output. In that case, when on the rising edge of the clock, the input will be copied, strobed to the output, because sometimes you can see in literature they use the word strobe for that. Then at that moment the input is copied to the output when it is strobed. Let's put this in this truth table. On the rising edge of the clock, and the D is 0, it will be output to 0. In the rising edge, if the D is 1, it will be copied to the output 1. And otherwise, in all other cases, so in any other point of the clock cycle, the output actually remains at Q. It's a clock, the rising edge, sometimes called the strobe. It copies D to the output Q, otherwise Q remains unaltered. Okay, so now let's go to our final circuit and have our positive flank edge triggered D-type master-slave flip-flop. I forgot to say here actually that once you use this kind of funny clock strobing signal schematics, which is now inside the box, then our latch becomes an edge triggered latch, and that is called flip-flop. So the final circuit that we have, positive flank edge triggered D-type master slave flip-flop, a complete mouthful, but I hope you understand it. What do? We take two of those edge triggered D-type flip-flops. One we call master, the other one we call slave. One gets the signal in and gets the clock through that funny clock pulse forming signal to make it edge triggered. And the other one gets the input from the first one, but also gets, look at this, the inverted clock signal. And that means that it now responds to the falling edge of the clock. So the master is responding, is active on the rising edge of the clock pulse, and the slave is responding on the falling edge of the clock pulse. So in this schematic, a time diagram, we have here on this horizontal axis we have time, and on the vertical axis we have the clock voltage. So on the rising flank here of the clock, actually the input signal is copied here to the intermediate stage, the Q of M, and this one is deactivated, so nothing is copied to output. But on the second half, on the falling edge of the clock pulse, this, which is now here in the middle, it doesn't change anymore, because this one, the first one, the master, is deactivated and has a stable output here, because we are not on the rising edge. But when we're on the falling edge, the first master is stable, has a stable output, and now it is copied by the slave to the output. So in summary, if it is on the rising edge, it's copied from the input to the intermediate, and on the falling edge, it is copied from the intermediate state to the output. And this way we have full control over what is going on in our circuit, because in very many circuits the timing is of utmost important, and that is why this is one of the most important circuits in digital circuitry. It's the positive flank edge triggered D-type. Actually, it is, I would probably have to remove this, because this one is positive flank and this one is negative flank. So let's call it edge triggered D-type flip-flop. I hope you enjoyed this and understand now a little bit better what are master slave flip-flops. See you in the next lecture.